Okay, then. Let's see. Cylinder slides along a stationary piston. What else do I have to say about that? We don't need to write that, but so, and then there's a cap that goes on. Well, I could write that because I'm telling you about it. And you're like, wait, what did you say? So once the piston is secure, the cylinder is capped. That's an important part. The cylinder is capped, creating an oil tight seal. Creating an oil tight seal. And I love the torque on this because you know I'm a very exacting person, and I like to appreciate that everything must be done to an exact spec and exact torque. So I'm going to give you the exact spec torque on here. Piston torque is, remember the piston's the thing actually holding it on the engine, is, and I'm going to quote the torque here, applying a force of 180 pounds at the end of a 4-foot, at the end of a 4-foot bar. That's my quotes. Applying a force 100 pounds at the end of a 4-foot bar while applying force. So you got somebody out there on a 4-foot bar and they must weigh 180 pounds. While applying this force, you will, quote, strike the bar close to the wrench, There's a wrench that goes in that you put the bar on. Close to the wrench with a hammer, weighing about 2.5 pounds. Weighing about 2.5 pounds. End quotes. So make sure you do it right.
This is really specific.
This is almost my favorite. Actually, this is the second. My most favorite is the one where it's, and I think I shared that with you, where it actually specifies what size man you need. You need a 175 pound man at the end of a, whatever was a 4-foot bar or something like that.
Why not a 175 pound woman?
Can't, said man. Must be specific. I got to move over. So Steven, you're going to tell me when you're done.
When it says close to the wrench, do they, like, what does that mean?
Okay, so there's a wrench that actually goes in to the in the cylinder. It goes on the piston, and then that just sorry, I don't think I have a picture of the tool. There's
you don't have a video of this?
I do actually. It's kind of a lengthy video that's like, it's fun. It's one of these old timey videos I'll show you, but it's basically a socket. It's a socket with holes drilled in the end of it, but it's a big old socket, about the size of my microphone and bigger than that. And so it's this big socket that goes over it, has holes drilled in it. And so then you put the wrench to these holes. I'll show you a video. Not right now. Okay, I'm moving on. Wow, half a page of notes already. Okay. In addition to all this stuff, there's this thing on here called a Welch bolt. Welch bolts. Welch bolts. They are, and I'll show you a picture, which I showed you already, but I went by it real fast. I am really not happy with why my controls for Zoom have suddenly decided to be completely different than ever before. Making my life difficult. All right, Welch bolts. Here we go. Welch bolts. So Welch bolts are these bolts that are hollow down the middle. And as the drawing says, you put lead wool in there, and then you put a plug or some sort of solder or something over the end of your Welch plug to keep the wool lead in there. And the purpose of the lead wool is for weight, so you can balance out the propeller. So sometimes you're going to find with these props, they'll be like, hey, look, it's a hollow bolt. Well, it's because the plug is missing, and that means that the wool is also missing. So you probably have an out of balance propeller right there. So we got the Welch plugs. Welch bolts, let me see. Hollow bolt, it is a hollow bolt that allows the mechanic to fill the void, with lead wool for balancing. You should see the kind of sheep it takes to get this lead wool from. They are really heavy. Takes a Welch plug, in the head to seal the bolt. In the head to seal the bolt. All right, so this is, I'm going to mention this here, and this is something that you have to know for all props, and all props are going to talk about the difference between dry and wet balance. So you want to dry balance. Dry balance is balanced with no grease. Balanced with no grease. And then a wet balance is with grease. Wet balance is balanced with grease. And I bring that up because I'd want to dry balance these props first, not add any grease or oil or anything, because that is just going to throw you out. And once the prop starts spinning and moving, the grease is going to distribute itself in a different manner. So I would want to do a dry balance it, do the lead wool, seal up the plugs, then add the grease. But I'm going to say this many, many times because this is the one place where you can really screw up a prop. On all movable props, that's constant speed, movable, anything, on all movable props, make sure you are very careful with grease. Make sure you are very careful with grease. So what do I mean by that? Well, do not overfill or over service. Do not mix grease. Do not, what was I going to say? Fill unevenly. But more than anything, don't overfill, or I should say over service. Over service. So make sure you know exactly how much oil goes, or oil, grease, what kind of grease goes in there, how you're going to add it. There's all kinds of procedures that you must follow very, very carefully.
Is greasing it like an annual thing, 100-hour, 20-hour?
Yes, all of the above. Depends on what the manufacturer wants. All right, adjustments. So it may come a time where the pilot would say, hey, you know, my too much RPM. I'm redlining my RPM. I don't like that, or I'm not getting the low end I want. And so you have to adjust the stops, and you can on these props. And actually you can adjust a lot of stops. It's part of what we do. And the way these are adjusted is this right here is actually the counterweight. You're looking inside the counterweight now. And there's a screw, a gigantic cover that goes over it that makes it look like it's some sort of solid counterweight, but it's not. You remove the cover, which is kind of heavy where it gets its weight. And it's got this particular set screw in here. And so the minimum and maximum blade angles are set with this, which limits the travel of the counterweight. So, so inside the cap, it's marked, I'll write this down, with the degrees. And well, I went through a whole example, which I probably won't with you guys, just for the sake of time and confusion. But anyway, inside there is where you can set the degrees. I gotta fix that slide. There we go. Okay, adjustments. Let's see, a minimum and maximum. Maximum blade angles may be adjusted. Angles may be adjusted. This is done by adjusting. This is done by adjusting stop nuts located under the counterweight crank. By adjusting stop nuts under the counterweight cap. The scale inside the cap is marked in 1/2 degree increments. Oh, that's actually, I'm sorry, 1 1/2. So marked in 1 1/2 degree increments. And this is an important point about that. The numbers are arbitrary. Arbitrary and do not correspond to a specific setting, And the base setting is usually stamped inside the cap, from the last overhaul, So I'll let you get caught up and I'll explain what that means.
It's almost better for me to just like listen to what you say and while I'm writing it.
Well, that's why I try and say it over and over while I'm writing so that guys don't have to look up.
Well, that and like, I don't know, like me personally, I don't like shortcuts. Like you put CW for counterweight.
Yeah.
I just have a phobia that I'm going to forget it in the future. Like, what's a CW?
Complied
So
with?
then
Clockwise?
Yeah, so I write everything down, like CTF earlier. I was like, what is that? And then when like we paused for a while and then you said it, I'm like, oh, that's what it was. And then I wrote the whole thing down. That way there's like no ambiguity.
Thanks to Kevin, I can be a doctor now.
What's that?
Thanks to you, I can be a doctor now.
I'm be an announcer now?
No, a doctor.
Oh, a doctor. Oh, the way my writing is?
No, mind writing.
Oh, okay. So what I was saying is that the numbers are in degree and half degree increments, and they're arbitrary. This 0 through 5 and 6 through 10 mean absolutely nothing other than they are degree symbols. So from 0 to half is a half a degree, from half to 1 is 1. So from here to here, it is 1 degree, but the 1 doesn't mean anything. But you have your base setting is stamped right here inside of it. So what does that all mean? Well, I think I write it. I can write it or I can say, I'll just write it. So, okay, so adjustment example. So let's just say the aircraft manual says for this particular aircraft, it should be, so aircraft calls for blade angles to be set at 17 and 22 degrees. And you notice that's not a lot. So we got 17 for our low pitch and 22 for our high. So we got 5 degrees separation there. So, so that would be 17 degree is low pitch, high RPM. And that would mean that my 22 degrees is high pitch, slash low RPM. And like in the example, we had a base setting, It was stamped in there of 25. So it's just, that's just where do you get this 25? It's measured out and it's stamped inside there from the overhaul shop. All right. And so it has to do with how everything kind of comes and fits together so that you can do the following. So if the base setting is 25, so if the base setting here is 25, that's base, and the angle should be at 27. It is 25 minus 7 equals 8, and that would be your stop nut location. So you have 8. So I'm gonna go back to this. There we go. So 6, 7, 8. So it should be right there at number 8. So you're going to take the stop nut, which is right here, and make it go to 8.
Which part, Kevin, used at the top of the head?
There should be a stop nut in there. My memory is that, yeah, well, the stop nut goes up and down. So I was thinking there was 2, but there's not. So it's just the one nut. It looks like it's just a bolt, but yeah, that stop nut will screw up and down on this and come to a stop. So I do have one in the shop that you guys will get to mess with. And so you just screw that down till you get to number 8. And then you're going to screw this one up too. We can figure that out. So if we want to do the other side, the high setting, so it'll be 25 minus 22 equals 3. So you're going to do the other one at 3. So you're going to set them the way you want them. Now you can't just set it and forget it. All right. So then you would have to, what is it? 1, 2, 3, I'll make this 4. So verify verify measurements with a prop protractor, all right, prop protractor, and then adjust, I should say fine adjust, fine, I'll make that fine adjust as needed to make sure blades are the same.
Hey, Kevin, I have a question for you. If you, since earlier you said the numbers are arbitrary and do not correspond to a specific setting, but you then said verify measurements with a protractor, but like that, each one represents how much you're gonna have to subtract, because in essence, that, like, for example, if it's 25 degrees of a base setting and the angle of blade is 17 degrees, then that 8 degrees is going to be the difference of the two.
Right.
So one of those numbers, in a sense, represents a difference in blade angle. Because if it's 17 is low pitch, even though there aren't really an in-between. So let's say it was like 15. So if it was 25 minus 15, it should be 10.
Yep.
Then you bring it up to 10. So each one of those corresponds just to 25 or to, see what I'm trying to say? Does that make sense?
No, I don't know what your question is, but I'll say this. So it's not that those numbers are necessarily arbitrary. They're there for a reason, but they aren't actual degrees. So if I need it for 17 degrees, I can't come over here and look at this and say, well, there's no 17, so I guess I have to throw it away. It's no good, right? There's no 17. It's 25 minus what you want gets that. So we had it at 8 and 3.
Okay, that makes more sense. Okay.
All right. What else do I have here? Got the Welch bolts. Got that. We got that. Oh, I've got some notes on tolerance, which I don't need to get into because then I might freak you out and think, well, I got to remember it. Inspection, same as any other prop. Inspect for leaks, cracks, security, all that other good stuff. So, all right, everybody's caught up with me?
How do you check for seals?
If there's,
You got to clean up.
yeah, if you're cleaning up the plane, if you have any leaks, it goes right down the prop blade and then slings itself all over the place, and it makes a really big mess. Okay, so everybody's caught up and ready to move on. All right, so that's the Hamilton 2 standard. So what we're going to do now is that is the end of the ground adjustable / automatic pitch change that in the 2-position prop. So all of those, a lot of them only had 2 positions, right? So like the Aromatic had pretty much the 2 positions. The Hamilton standard we looked at, 2 positions. The Beach Roby had all kinds of positions, but you just moved them with a little either a crank or a little electric motor. So now we're going to get into where everything went to, and that is the constant speed propellers. And we're going to spend pretty much the rest of the class period talking about constant speed and going through them and the various types and how they work. There's some tricks to learning them, which I'll show you as we go along. It just makes everything real simple. I'm like, oh yeah, that's just, I can throw out any prop at you and you're just going to ask me 2 questions. Does it go on a twin? Is it counterweighted? Yes or no? And I'm like, yes. No. And you're like, well, then that's how it's going to work. I don't care. And you'd be right. So, but in order for a counterweighted prop, let's try that again. In order for a constant speed prop to work, it needs a governor, because the whole point of a constant speed propeller, as its name implies, it keeps the engine at a constant speed. So once I set the lever at a certain RPM, in theory, I can pull back on the yoke and start a climb, and that prop is going to do whatever it has to do to keep the engine at the same RPM, which means if I start a climb, it's going to flatten out to keep the engine at the same RPM. If I dive down towards the ground, it's going to do its best to give me massive amount of pitch to try and slow it back down. So it's always going to be hunting and choosing the exact same speed. Now, of course, it's going to do that within reason. So if I point at the ground a little bit, it's definitely going to give it a higher pitch to slow the engine down, because naturally the engine is going to want to speed up. If I pull back and start climbing, it's going to flatten out the prop, because naturally the engine's going to want to slow down. So it keeps it in this same RPM at all times, which means you've got to have something that knows what the RPM is. And that's what the picture is right here. These are all propeller governors. So these propeller governors are the sensing mechanism that keep the propeller where it needs to be. So the governor is going to do two things. Two things at a minimum. One, it is going to sense the engine RPM and tell the prop what to do. And two, it is a boost pump of very large proportions. It is going to boost the engine oil pressure up to in the hundreds, 250 or more PSI under most circumstances. So there's a lot of pressure behind these. Now, we looked at the Hamilton Standard 2-speed a minute ago, and it just took engine oil pressure at 60 or 70 PSI and just dumped it right into the prop. And that was enough to do what it had to do, and it just kept it on there. But we need more oil pressure now, and we need this governor to know what to do. And it's going to do it very similar to the Hamilton Standard. It's just going to boost it first, and then it's going to send it to a selector switch that is automatic. It's just going to, and it's the same thing as we saw before. Now it's just a selector switch that's automatic. Before, the pilot had it, it would be increase pitch, decrease pitch. This is going to do the same thing. Boost the oil pressure, send it to control that simply says increase or decrease. Well, but we're going to add a little bit to it. So now it's going to have three options: increase pitch, decrease pitch, or don't do anything, which can translate into drain oil, add oil, block oil. And that's how I'm going to say it: drain, add, or block. Now, depending on how the prop's designed, the draining may make it go high pitch or low pitch. The block does block, and the add oil may be increased or decreased pitch. So we're just gonna have to look at that and see which way is it going. So that's gonna be the governor. We're gonna go through the governor now. This particular governor's, this one's got some gears attached to it, which tells me that it's off of a twin, and that is a synchronizer. And we'll talk about synchronizers the last thing, but and how they work. But a synchronizer makes sure that the propellers are turning at the same speed. It's very, very difficult if you have a twin to get the exact same speed out of them. And so with the synchronizer, you can turn it on and it will actually sense which, it has a master and a slave. And so it'll adjust, and this is the slave one, obviously, it'll adjust this one to match what the other side's doing. So it gets quieter in the cockpit. You don't have resonant frequencies. And these other two are pretty much the same thing. It's just this one to the far right. It looks more like a modern one that I would see on a Continental. And this one in the middle here looks like something I would, an older style that I would see probably on a radial engine of sorts, especially with this big old arm on it. All right, so talking about the prop control, that's the blue knob now. And I showed you in the video, and hopefully you guys remember, because I don't really have it queued up to go, but you have to remember that the forward position is the all the way go fast, right? So that means high RPM, low pitch. And when I start up the aircraft, I'm going to want to always have it up there. The exception is the Hamilton Standard. It goes the other way just to block it, right? But otherwise, you want it all the way into low pitch for starting all the time. Low pitch, high RPM for starting. And when I start it up, that's great. And I can move the prop, the black handle, the throttle, all the way from idle to high RPM. And what I'm going to see, it's going to act like a fixed pitch prop for the most part. You won't know the difference. I'm going to see the RPM come up, and I'm going to see RPM go up and down with the throttle. The big difference between is, if you were to blindfold me and all I could see was the RPM gauge, I could tell if it was a constant speed prop or not, simply because, remember, in a fixed pitch prop, when I go to wide open throttle, this right here is redlined at 2,700 RPM. I should see static RPM somewhere around in here. It won't go any faster than this arc right in this area here because it's a fixed pitch and the pitch hasn't changed, and it's going to hold it there. In a constant speed prop, it's going to go right up to and sit right at red line because the propeller is designed to do that. It will be flattening itself out. And so it's on its low pitch stops, and low pitch stops give it red line RPM at static. So there is no checking static RPM with this. By the way, notice that? I haven't before. Why is it red between here and here?
I was just going to ask about that.
Because that's the no zone.
That's the no-go zone. There's some sort of resonant frequency problem with this aircraft. So you cannot be in that area because of resonant frequencies. And I bet if we could read this, it says something to the fact of something operation, avoid continuous operation below 13 inches manifold between, and it's got that and that RPM. So it's also got a inches manifold. Okay, so also in a constant speed propellered engine, you will always have a manifold pressure gauge. And the reason why is because once I'm up and flying and I've got my black throttle set somewhere where I want it, and I start pulling back on the RPM is going to start slowing down, and the blue knob is going to hold the RPM exactly where I want it. And now the black knob is the manifold pressure. So I can go ahead and mash the black all the way forward, but my blue is going to say, no. So if I pull this back and set it at 2,500 RPM, I can take this throttle and push it all the way forward. It's going to stay at 25 RPM, but you'll see the manifold pressure increase because I opened up the throttle. If I start pulling back on the black, it's going to hold the prop still at 2,500 RPM for as long as it can. And I'm going to watch the manifold pressure go down, 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 down. And then at some point, there's just not enough power, and it will flatten the prop all the way out, and it'll start to decrease RPM because I pulled this back. So the two work hand in hand, and you have to think about what it is you're doing when you're doing it. So, okay, so the reason why I have these pictures up here is to explain to you how the oil gets through the engine and around. So this is a Continental, and they drive the governor right here. So the governor is driven off of this gear, and you can see right down here, maybe some studs sticking out. Those are the studs where the governor is going to mount. So the governor is sensing engine speed directly off of the camshaft. And it doesn't really matter what it's sensing it off of. It's just set up to sense it off something on the engine. Lycoming puts it off the back and runs it off of another idler gear. So it's not relevant where it's being driven, and it's not relevant at what ratio it is. Trust me that it's a different ratio than something the crank. It's at a ratio. It's at a different speed, and it's not important what the speed is. What's important is that it is sensing speed, and it's set up by an engineer to know exactly how fast it should go. So in a Lycoming, in a Continental, this color, the gold one, this particular one, the Continental, what happens is the governor, the oil comes, what's my next picture? I gotta get this out of the way and see what my next picture is. I don't know. Okay, so there's an oil gallery that goes right up to the governor. It puts oil into the governor, and then the governor gears pick it up, boost it, and shove it right back into the crankcase through a gallery that it goes into. So the gallery, I don't think you can see the gallery. You really can't. It comes right up through here. It's a hidden gallery right here. And this is called a transfer collar. And that transfer collar is picking it up right off of there. And that's what I had a picture of right here. So here's the transfer collar. And there's a little nipple that goes in here with, it's actually quite small, that has O-rings on it. So it's transferred right through here, through this, into the transfer collar. And around this transfer collar, inside of here, it has the high pressure oil. So it's 250 PSI right inside there. And then the crankshaft is running around in there, and it inside of that crankshaft, on the crankshaft, right about here somewhere, there's one little hole. That's it. That hole directs oil to the inside of the crankshaft. Now, of course, it doesn't matter that there's only one little hole, because that one little hole is always running around inside of the groove in there. So it doesn't matter. It doesn't care, and it doesn't know that there's just one little hole, because the pressure is always finding that hole and making it go up here, in, and around. Now, I tell you all that to tell you that you also have to think about the fact that there is space right here between the oil transfer collar and the crankshaft. And as the crankshaft and that collar wear, you're going to get leakage out of the governor. And I also tell you this to tell you that it would be probably impossible for the governor to be in a hold the oil position for very long, because the prop is always trying to bleed it back out, and it's going to find its way and leak out. So the governor's always got to be putting a little amount of oil into the engine and through the transfer collar, just because of leakages and slippages and stuff like that. So this is the continental way of doing it. They have the oil transfer collar. I like that. Lycoming, you guys did not have a bearing like this, but a lot of you read about these bearings. And so I found this picture where this guy used some sort of rope here to seal his crankcase, and it probably didn't last very long on the internet. And so it just has a very long bearing. And at one point, we'll say it's this one here. I can't remember exactly where it is on here. Oil is transferred right through here, and you can see the hole lined up right there. So it's got the same thing. It's got a groove cut in here. And so it just makes the oil transfer collar out of the big bearing. So one spot right here, we'll say, has got the groove where governor pressure is. And then over here is the grooves where normal oil pressure is. So the same thing comes. You have oil pressure. It's really high. It's going to leak off into the rest of the bearing. Just a lot of pressure there. So it's just what it does. So, all right, so how does the governor work? Well, we'll start with a very simple drawing here. And I will pull up a pin because I want to. All right, so pin. So let's identify where we have here. So we have engine oil inlets, propeller line, pilot valve, flyweights, spring, spreader, relief valve, gear boost pump. Okay, so to make it very simple, we're going to have engine oil is inlet. So this is from the engine main gallery, right? And it comes up and it goes through here, and it's going to go to the outside of the gears and get pumped up into here. So once we get into here, we have very high pressure oil, and that's just how it does it. So boosts it, pumps it up, sends it right here, and now it says, okay, now you've got your high oil pressure. What do you want to do with it? And again, you have three choices. So it's either two prop, or I should say oil to prop, oil from prop, and no oil movement, or no oil movement. I often just say blocked. Blocked. Okay, so in the blocked mode, what happens is this is the prop line. So it's going to go back and forth. This is to and from prop. So to prop and from prop. It's got to do both. So in the blocked mode, it comes up and it hits this pilot valve that goes up and down. And right here, it comes up and it tries to go somewhere and it goes nowhere. So right now, this is actually shown in the blocked position just by looking at the pilot valve. And so that means blocked also means on speed. So, and that doesn't last very long because it's like I just showed you, it's going to bleed off somewhere. So this particular one is on speed. Now I can't really say to you right now, to prop is increased pitch or from prop is decreased pitch, because it really depends on what kind of prop you've got on here. So, but we'll just kind of go with something here and say pin. So let's just say that we go under speed. So in the governor, it knows three things. It knows on speed, it knows under speed, and it knows over speed. That's its brain. So it's kind of like a guide. We are either hungry, not hungry, or thinking about being hungry, probably. I don't know. So, all right. So on speed, under speed, over speed. And the way that you know on speed or under speed is going to be by the flyweights. If the flyweights look like that, like they are right there, that is an on speed. These flyweights are balanced between a spring pressure and centrifugal force. So this right here, this cup is spinning around in a circle very fast. It's a little merry-go-round, and it's unfortunate that most of you are too young to remember the good old-fashioned merry-go-rounds where were made out of metal on a really highly polished bearings where you could get them spinning at 100 miles an hour and fling yourself off. And then you'd appreciate this, but I think we talked about this video before. So when this thing is spinning, if it spins too fast for the spring pressure, the flyweights will start to come out like that and start to lift up the spring. It'll start to lift up that spring because the weight on this, the centrifugal force is forcing it out and it forces that up. So I will say that is an overspeed. Overspeed looks like this. And I kind of write these pictures out like that. So there's overspeed. All right. Well, there's also underspeed. Underspeed. So if the spring pressure is too much, then it's going to overcome this, and the flyweights it's going to push this part down, and the flyweights are going to rock themselves in. I'm exaggerating there, but so that would be in an underspeed condition. They will come in. So in class, I do that nonstop. I go, okay, well, it's underspeed, on speed, overspeed, on speed, underspeed. So the flyweights are just being allowed to move around, and they're balanced out by this. So we could say in this particular case, we'll just see what happens, and we'll follow it through and just go with it on this particular drawing and how it's done. So, oops, I wanted an eraser, and I keep doing that. What if I do? There we go. Okay, so let's just go through and say, what happens if this goes into an overspeed? I should have just left it where it was. We'll say it goes into an overspeed. So an overspeed, this cup here spins around because this is driven right here. So this is the part that bolts onto the engine. And so this is spinning around very fast and sensing engine speed. And of course, it's the driven gear. So this means the driving gear, driven gear. So this is being driven by the engine. So this is all spinning around at relative to engine speed, and it gets too fast. And so my counterweight, because the centrifugal force flings out and it overcomes spring pressure, and it makes this pilot valve go up because the pilot valve is attached to this. And so it lifts the pilot valve up. Well, when it lifts the pilot valve up, it's going to lift this piece up a little bit out of the way, and oil then comes up here and it drains off, and it goes right, so then it drains off. So in this particular configuration, an overspeed is going to make oil drain in this configuration, oil drains in this configuration. Not all of them. Sometimes it's the other way around, but in this one, it's going to make oil drain out. And so I already showed you what happens when we're on an on speed, oil is blocked. But if we go into an underspeed, say I pull back on the yoke and I start to climb, well, then that means the engine's going to start slowing down. And so the engine slows down, and so the spring pressure wins, and it pushes down on the counterweight, which means the pilot valve goes down. When the pilot valve goes down, this little section right here is going to drop down to here, opening up this passage, and this high pressure oil that's been waiting this whole time while I've been talking is going to come through here, and it's going to go to the prop, and it's going to have oil to prop. Oil is going to come down, and that means in an overspeed, it will be oil to prop. Oil to prop. And that's what's going to happen. And then we go back into an on-speed condition. So now we're in on-speed. So on speed, and that's what it's showing because the little counterweights are right there, perfectly in line, the flyweights, I should say. Flyweights are perfectly in line. Well, we do have to discuss something. We've got oil coming up here being pressed, and I've got, what, 250 or more PSI right here waiting to go against drive gears that are constant displacement gears. That's going to be a problem. But fortunately, there's a relief valve, and it'll just open up that relief valve, and it just comes back in here and through a series of passageways is just going to enter back into here and just recirculate. And so it recirculates until it's needed. And these things are incredibly noisy. You're going to be shocked at how loud these things are when you guys actually get to run one. So that is how this works. Let's look at, I think, my next slide. This might be a little bit more difficult for you to look at because it's a little blurry because of what's going on here, but we can just run through it real quick. I have a few minutes before break, right? Somebody will I don't have my clock on my computer the way things are set up, so somebody will yell at me when it's time to go. Okay, so things I know: underspeed, overspeed, on speed, underspeed. Why are there two underspeeds? Oh, that's feather position. We don't need to know about feather. That's why. So, okay, ignore that for now. Just confuse you. So, underspeed position. Underspeed, this particular one has oil comes through and it recirculates in the underspeed, and the pilot valve has let oil drain down. Like, this is a good picture. That's really realistic how it really looks inside. So underspeed, oil drains from prop. I go into an overspeed. We'll go down here. On speed. On speed should block it. So here we go. We're still in recirc. Oil coming back from the prop line is coming in, and it does nothing. It's completely and totally blocked. Once it gets in here, it can't go up, can't go down because it's blocked right there, and it's blocked right there. So it's in a blocked position. Then I go into an overspeed because these flyweights have come out. I'm in an overspeed. It lifted up the pilot valve. Oil comes in, goes through my gears. Pilot valve is now lifted right there. See, it's right there blocking it. Now it's lifted and it goes down into the prop. Also, when it lifted it up, it has to keep this passageway blocked. Otherwise, it would just drain out through, like right here. So it's got to move up and block that. And this little, I don't know, that little thing right there, there's just three little pieces of metal that pilot it and keep it from chattering around inside. It's wide open there. So we got that. And then I know your book has just some other basic pictures that kind of show it. And I think I like this one because it reminds me to tell you that this is really what the blue knob is. It just increases or decreases spring pressure. That's all that blue knob does. It has a rack and pinion with little gears right here. So the gears, when I pull back on it, it is going to say back is high pitch. And so it's going to pull this up and release spring pressure and let the flyweights move out a little bit. So I'll say it's in an overspeed and give it more pitch. It's exactly what happens. So I'll say it again. So I pull back on the blue knob, which tells the engine that I want to pull back on the RPM. I want to slow the engine down. Pull back on the blue knob, slow RPM. It will release tension on the speeder spring. When it does that, the flyweights say, oh, we just went into an overspeed condition. How do you correct for an overspeed condition? Add more pitch to slow the engine down. So it's going to add more pitch and bring these back in. Follow? Hope so. What do I got here?
Hey, Kevin.
All right. What's that?
How are the flyweights connected? Is that like a pin or something?
Little pin.
Okay.
Yep. So I think it's break time.
Yep, it just became 4:20.
All right. So it'll probably take me 10 minutes to find out where my controls went. All right. So I will see you back in a couple minutes.